Relational databases are used by most applications. MySQL, Postgres, Microsoft SQL Server, and other products implement the core features of a relational database in different ways. A developer who has never studied this space in detail may not know the differences between these databases, and in this episode we describe some of the trade-offs that relational databases can make in their implementation. Craig Kerstiens is an engineer at Citus Data, a company that makes scalable Postgres. So he is an expert in databases and scalable architectures and distributed systems that go along with databases. We talk about the requirements for a relational database, ACID compliance, how different databases handle different distributed systems problems, as well as the recent blog post from Uber about Uber's switch from Postgres to MySQL. There's also an upcoming episode about Uber's switch to Postgres with Evan Klitsky, who wrote that article about the switch. And with that, I hope you enjoy this episode, Relational Databases with Craig Kerstiens. DreamHost Cloud gives you fast virtual machines and storage for a low price. DreamHost Cloud brings infrastructure as a service together with 24/7 support and a great community. The DreamHost Cloud platform is all based on open source code that uses OpenStack and Ceph. Go to dreamhost.com/sedaily to deploy your application today and support Software Engineering Daily. With the easy-to-use UI, standard API, and a powerful SSD infrastructure backend, DreamHost Cloud has everything that you need to deploy and maintain your application. The billing for virtual machines is simple. Only 600 hours are billed max per VM per month with 100 gigabytes block storage included, and free bandwidth for a limited time. It's easy to try at dreamhost.com/sedaily. Deploy your application to DreamHost Cloud today. I know you've got that side project waiting for its deployment, and when you decide to deploy it, check out DreamHost at dreamhost.com/sedaily. Thanks to DreamHost for being a sponsor of Software Engineering Daily. Now let's get on with this episode. Craig Kerstiens is an engineer at Citus Data. Craig, welcome to Software Engineering Daily.
Thanks, glad to be here.
So today we're going to talk about relational databases, and we'll get into some different types of relational databases. But let's first start by talking like at a general level about relational databases. What are the requirements for a relational database?
Sure. I mean, I think at the top level of it, you look in and, it's, if you think of it as a Excel spreadsheet, right, where you've got data in one sheet that's very flat, but it may need to relate to another one, right? And you start to reference stuff in other sheets. So you reference that sheet by name. Basically, you've got relationships there between different tables, right? I think that's pretty straightforward to follow. And relational databases have been around for 20, 30 plus years now. And at the core of any application, right, you've got models that relate to other ones. That maps very, very cleanly to a relational database. I think in any application, whether you're using a relational database or not, you have relations, right? It's a matter of how you manage them. So there's a concept of schema on write versus schema on read. Schema on read is something that kind of came out of more of the Hadoop space, where you've got flat files sitting around. Then you tell the system how you're going to read that data and what the file structure is. Whereas, with traditional relational databases, you've got the schema on write. You've defined your schema ahead of time, and you fit the data directly in there. At the end of the day, there's still a schema. It's just a question of when are you managing it.
Got it. So how is a relational database typically representing its data on disk?
So it varies quite a bit system by system. With Postgres, you've got something called a tuple, or basically a row. You've got, that's one record within the row. You've got a full record, which is the full row. You've got tables, and then within there, you store basically sets of data. And within those sets of data, they're on Postgres. I've got to double check the exact size, but I believe it's about an 8 kilobyte as a single page. So that's the smallest thing you're going to write out. And within there, you might have multiple different rows and how they relate together. And then within one table in Postgres, it's a single file. You can't easily go and kind of poke and inspect that file, but it's one file there that exists on disk. And then from there, you've got things like indexes that point into these specific tables and that kind of thing that gets layered on top there a little bit.
Sure. So different relational databases, they all have different ways of performing these basic operations that we associate with relational databases. We've got insert, update, delete, and so on. Are the different relational databases, do they have like significant differences in how they implement these different methods?
Somewhat. I mean, absolutely under the covers, right? You look at a system that's been built for 20 years, and it has a lot of kind of foundational bits in it. At a really high level, if you look at kind of the two major sets of relational databases there, and I say major sets, Postgres does things one way, and I think a couple of the other major ones like Oracle and MySQL score data a little bit differently. And this comes under the covers and how it basically handles ACID semantics. Okay.
So what about caching? What are the requirements for caching that we need in a typical database?
Yeah, so this varies a little bit, again, database by database. The Postgres approach is let the operating system cache do quite a bit. It's really efficient at that. I'm not exactly familiar with all of the internals of Oracle, but Oracle does a good bit more of kind of handling the cache for you. The rule of thumb I would actually say is even when you're dealing with a relational database, you still want most of your data in the cache. So, or at least for OLTP applications or a standard web application. If you're dealing with OLAP or analytics or data warehousing, it changes a bit. But the key there is that even if you've got a terabyte of data, you want your frequently accessed data in memory. And Postgres is going to do this automatically for you. There's multiple layers of cache. There's some Postgres layer, then there's the operating system layer. But essentially what it's going to do is say, anytime I read this data, I'm going to keep it in memory in the cache. And it's going to be pretty intelligent about that for you. Now, as soon as that data falls out of cache, performance on something like a web application is going to go from, maybe a few milliseconds down to possibly seconds, because it's got to hit disk. And as we know, when you read from disk versus memory, it's going to be massively slower.
So what's the typical interaction between the database cache and the page cache? You mentioned the operating system page cache.
So it varies a little bit there, right? So with Postgres, it's letting a lot of the operating system page cache, which is automatically, if you remember I mentioned kind of there's a page, which is a set of data on disk. So in Postgres, that's an 8 kilobyte page, right? Which is actually a representation on the disk itself. Postgres is letting, if that page is in memory in the database, or excuse me, in the operating system, it's automatically pulling from there, so it doesn't have to hit disk. So with Postgres, basically that page cache and how much you allow the operating system cache to have determines how much you can actually store there.
What about schema updates? How does a relational database typically perform a schema update if the user wants to add a column to the schema?
So essentially what it's going to do there is going to come through and say, within this database, add this column to the layout of the table, which is kind of in that top page there. And there's an important detail there if you're an application developer. So with something like Postgres, if you add a new column and you say, okay, it's here, all new records are going to have that one, all old records may still have that column there, but no data, it doesn't actually have to do that much. It only basically kind of creates that new schema, that new layout, and then saves all the data for new records. The reason I say it doesn't have to do much is because if you don't write out a new default, it's not going to have to rewrite all of that data. Now, this can vary some based on different databases, but for Postgres, that approach is extremely fast. If you add a new column, it's almost instantaneous. Some other databases, when you add a new column, it actually does require a full rewrite. This is actually kind of a big knock against some other databases, that you can't add a column, and I can't say without any locks. There is a lock there, but it's a few milliseconds. But if you add a column with no default, that's pretty fast. As soon as you have to rewrite that data, then you have to rewrite the table on Postgres. Does that make sense?
It does. So we're often replicating our databases for one reason or another. What are the typical reasons for replicating the data in our databases?
Sure. There's a couple different reasons I see. One is for higher availability, right? So with a database, if you've got a single node and it goes down, your application's down. There's a number of ways of replicating data. In a sense, a backup is a replication, right? It's just delayed by whenever you took the last backup. The more common approach is actually streaming the data from one node to another. And that can be done for high availability so that if that one node goes down, you can immediately fail over to it. I've also seen it done for other things. If you're setting up a read replica, it's really common to give this to the BI guy or the data analyst that wants to run queries on that. And the reason you would do that is not just for read-only credentials, but if you remember, I talked about that basically your cache being warm and frequently accessed data and being in memory. If you're dealing with a data analyst that wants to run, say, maybe a count star across your entire data set, all that data is going to have to be read at some point, and it's going to bust your cache. So for a web application that's frequently in use, you may not want them operating their analytics on the same database.
Okay. So there's this feature called multi-version concurrency control that a relational database needs. Explain what that means and why does a relational database need this feature?
So MVCC, or multi-version concurrency control, is probably a difficult thing to explain out loud. But the idea here is you've got two things happening at the same time. You have to know which one takes precedence, right? If I have a user coming in, say my wife and I share a Spotify playlist, and we're coming through and I add something and she deletes it, or I update the name of the playlist, then she updates it at the same time. Which one of those happens, right? Because basically we're trying to do an action on the same record, then one of us should actually get to have that to happen, and the other one should say, wait, this was already changed, what's going to happen now? So MVCC, what it does is basically says, I'm going to see, you can read anything that is happening after a certain point. So in Postgres, this kind of gets down into some of the internals. So what you can have is a transaction start to write some data. And with Postgres, there is a set of transactions IDs that exist under the covers. So every new transaction gets a transaction ID of its own. So even something like an insert, an update, delete, a one statement one still is a single line transaction in Postgres. Now, if I'm doing multiple things there, so say I do, begin, probably what you more so think of as a transaction within a database, and I start to do a bunch of commands. That begin is going to get a transaction ID. And now if I'm a developer on the other side and I come through and read data, I can only see what's happened before that transaction until that transaction is committed, if it's relating to that data at all. Now, other transactions can come in and insert and alter data, and that new transaction is going to get a new ID saying, this is my ID, but I can't commit anything that alters any of this stuff before until that other one is committed. And if there's an exception there, it's kind of going to blow up and say, nope, you can't modify this until you actually come back through and grab a new transaction.
Okay, so multi-version concurrency control is sort of when there's two threads that are accessing the database. They may be involved in transactions that began at different times, and in between those two times, maybe a certain row was updated, so those two threads might have different perspectives on what the state of the database should be.
Right. And they're essentially, MVCC's big win is really on the read side when you talk about it of, okay, I can see data as of this time, I can see data as of this time. And then it's basically a mechanism for resolving when you're working on two records that need to resolve in some way. How do you do that?
Okay. So when a new row is going to be written to a replicated Postgres database, the data is first written to a write-ahead log. What is a write-ahead log?
So the write-ahead log in Postgres is essentially one giant append-only log. So anytime you write data in Postgres, update data, or delete data, it's going to write out a new record in the wall log, or the write-ahead log. If you delete a row, it's basically going to write a new record saying the old one's dirty, here's a kind of an empty row there. Now, under the covers, it's actually a binary format. And this is written to disk and basically is the entire state of the database. Okay,
and so what do we do with the write-ahead log? Like if a server goes down that had had one of our database replicants on there, what do we do with the write-ahead log?
So the write-ahead log, coupled with a couple other things, can give you better data durability. So if your database goes down and you had what's known as a base backup in Postgres. So there's two types of backups that are pretty common with databases. There are logical backups, which is like a PG dump. That is the actual SQL statements to go and create your database. So if it's kind of what you'd expect of a create table, a bunch of inserts. That is your database at that state in time. There's also base backups, which are the physical bytes on disk. And what you can do with that coupled with the wall is restore your database to any exact point in time. So with a base backup, you've got your write-ahead log, which is all this stream of events that's happened, from writes to updates to deletes. And you can replay that to get to the exact same point of time that you were at before. We actually wrote a tool back when I was back at Heroku, and the engineer that wrote it there is now at Citus Data, called Wally, which is a tool for helping you kind of manage those. And it archives that write-ahead log to S3 for you, so you kind of don't have to worry about managing all of it yourself.
So you've been talking about Postgres, but we're talking about relational databases more generally right now. Do all relational databases have a write-ahead log feature?
All don't, but all have some kind of notion of kind of what is the log under the covers of it and how it works, right? So I don't know that all have basically a write-ahead log, but many have some similar concept. And part of this actually depends on how is data updated under the covers, right? So Postgres, MVCC, and the write-ahead log is pretty key and fundamental, but in some other databases it works a little differently, right? So more generally in relational databases, another common model is when you delete data, you don't write a new row. You basically have a reference to you basically say, okay, we deleted this row, and if you want to undo that, you have a rollback. And so this is more common with MySQL and Oracle, and it has different trade-offs there, so that when you delete data, when you update data, it doesn't generate new data, so it's generating a little less, but it also has different kind of trade-offs in how much you're able to read as well.
Okay, you mentioned that the write-ahead logging helps with durability. I think I've also heard you say that it can help with atomicity. How can a write-ahead log help with atomicity?
Yeah, so there essentially what happens is you're not going to write to the write-ahead log unless the entire transaction happens. So I think I've mentioned ACID and atomicity and durability a little bit. It probably would make a little bit of sense to kind of walk through what is ACID, because I think it's pretty key to relational databases. So the idea here is like atomicity means if I've got a transaction, I do begin, then I do 3 steps, and something crashes, or I didn't commit, or my application web server fails and it never commits. The database isn't going to see any of that. It's basically going to say, okay, nothing happened. That first statement didn't happen, the second one didn't happen, the third one didn't happen. That's kind of at the core of, what is the idea of a transaction, right? Either all the transaction happened or it didn't. So you can't be in this weird state of, I started to create a user but didn't set their password or something like that. We'll get to durability in a minute. I'll walk through actually in order. So consistency, guarantees. By
the way, for those who don't know, ACID is an acronym, and so it's atomicity, consistency, isolation, and durability, right? And these are features that a relational database can have.
Yep, exactly. And so consistency is probably less common for web developers, but it's the idea here that it's going to bring your database to a very consistent state. So this matters for things like constraints and triggers, right? So if you've got a foreign key constraint, you can't run a transaction that then violates a foreign key constraint. It's going to blow up and say, if you're I'm trying to think here. If I'm trying to make a purchase in a shopping cart, I have to have an account, right? I can't go and, start to create that account later. It has to be there, right? Isolation guarantees that essentially, this kind of comes back a little bit to that MVCC, that results were executed in order. So that if I do one thing, then the other, it's all in this kind of consistent state of a single transaction there. Again, that's one I think that you don't think too much about, that, this happened, then this happened in this other transaction, then this happened in this other one. But those should be able to be applied in a very consistent serial order, one after the other. And then durability basically means that once you've committed, that data is guaranteed there. So while we're talking about the write-ahead log in Postgres, talking about crashes, with Postgres, once data is written and we say it's in the wall, that means it's written to disk. Something like a purely in-memory database doesn't have durability, because if the instance crashes, it's gone from memory and you don't have a permanent record of it. That's perfectly fine for a lot of applications, but this basically means that, hey, I've written it to disk, something that is, more durable than memory of a system.
Right. Okay. So we have been talking about relational databases in the abstract. One thing that has changed in relational databases over the past 10 to 15 years is we've moved them into the cloud for the most part. What has changed about how we architect and use our relational databases as we have moved them all into the cloud?
I think one thing that's changed is it's actually made development a lot easier. I look in, at Heroku, we used to joke that, running web applications, that was kind of the easy job. Maintaining state was the hard part. So if you're familiar with 12-factor application, the idea of separating, your stateless applications from your stateful parts, and the stateful part is the database. What I think we've seen, though, is also kind of an explosion of different databases, right? Whether it's NoSQL ones or new relational ones, very specialized ones. As we've gone to the cloud, we've been able to get a lot of expertise around databases that's siloed there. At Heroku, what we saw, when I left there, we were managing over 1 million databases. For us, a 1 in a million issue was almost every day. But what we were able to do is concentrate some of that knowledge, deliver it back, and give maybe someone that wasn't a DBA, someone that wasn't an expert, more knowledge on what they needed to do and pay attention to. So giving them better tools for looking at performance, looking at how to optimize queries, all those sort of things. And overall, it's just kind of accelerated what they're able to do and how we're able to develop with them.
Now, is that because since we've moved databases to the cloud, so many of the maintenance and uptime guarantees that used to be on the operators who were running the databases in their own data centers, the onus is now on Heroku or AWS or whatever the company is that's running that database?
I think a little bit is some of that and some of the expertise. And I think, as a smaller company now, you're able to go a lot further than you were before finding that DBA, right? DBAs aren't a dime a dozen. They're often harder to find. They're, not to stereotype too much, but usually you're gray-bearded people that have been around for a while. And in general, they're just hard to hire for. So I think a little bit is that, yeah, you've got some of that other expertise there. I also think, it's shifted the model a bit. So for me, being a database guy, data is probably more important than your application code in the sense from a security perspective. Like, it's bad if my code gets compromised, but it's really bad if all of my user data gets compromised. So one thing we've seen, I think, as cloud providers have grown is that they're treated now more and more like a distributor of databases. So things like security notifications, they're paying much, much more attention to, and often getting kind of advance notice, right? Versus you as a small shop, you wouldn't have that kind of benefit of, is there a new security patch coming for Postgres or MySQL or Oracle? They're getting that premier treatment and able to actually patch you in a safe way ahead of time faster than what you could do on your own. So it's not necessarily particular to databases, but I think databases have benefited very, very heavily from that specialization and concentration of knowledge.
So we've discussed relational databases in the abstract. And when we're looking at these different relational databases, there are different ways to implement some core features. And I know this must be true because there are so many relational databases. There's SQL Server and MySQL and SQLite and Postgres, of course. What are the types of trade-offs that these different databases are making?
Yeah, so there's probably a lot in there. I think if you look at pretty much everyone you just listed, they've all been around for almost 20 years now. So I think a lot of those trade-offs were made a long time ago, and I think each of them has slightly different benefits, right? So with Postgres and its MVCC model, there's more of an expense in deleting and updating data. At the same time, a big knock against Postgres 5-10 years ago was vacuum. So basically, as you deleted data, it still wrote out data, and then it had to come back through and kind of clean up this logical delete. vacuum has gotten massively better, so it's not quite as big of a bottleneck these days. In contrast, I look at MySQL and SQL Server, and they've come a long way in their read performance, which is kind of where Postgres focused first, in their read performance over the same kind of workloads. So in general, I see they're converging quite a bit. I think what's probably more interesting is to look at some of the end user features that are coming along, right? So while we're talking a lot about relational databases, I think there's this shift to how much are they relational, as a end user, and how much can you get some of the ACID guarantees, but then start to support some of the things that people liked about NoSQL, like flexibility with your schema, the ability to do things that are more than SQL and index in different ways. So I think they're actually coming along pretty well there, and that's where the more interesting spot to pay attention to is.
Yeah, this is the domain that people talk about as new SQL. That's the buzzword term people use, I think, to describe what you just said, which is the benefits of relational database, the classical benefits of relational databases, together with the benefits of NoSQL databases, namely the ability to update the schema easily as time goes on. Would you say that's accurate?
Yeah, I think so. And I think, in the new SQL, I think there's a whole lot of things in there, right? I think if you look at its most basic level, what people really, really like and trust about traditional relational databases is they're very safe for your data, right? They have certain guarantees of what a transaction is. When they write data, it's there. What application developers especially don't always love is some of that rigidity. And that actually, while it is kind of coupled in a way, a lot of them more and more, especially Postgres, but even some of the others, are starting to take a little bit more of a liberal approach to what you can do there in terms of flexibility.
Right. So we should talk some more about Postgres because you are an expert in Postgres. You work at Citus Data, which is a company that works on Postgres. So why don't we just start with what is Postgres?
Sure. So Postgres is a relational database. It's been around for actually 20 years now. It comes from the same root, sort of, as some of the other ones you mentioned, such as Sybase and SQL Server. So Postgres or PostgreSQL, Postgres is a perfectly fine synonym for it. That's actually been debated and discussed a number of times that PostgreSQL was one of the biggest mistakes the project made, just in terms of naming, because it's quite confusing. But Postgres came out of UC Berkeley, and the name is for post ingress. SQL Server, Sybase, a number of others kind of have their roots in ingress, and it was really one of, if not the first, relational database. So Postgres is kind of the successor to that. It's been around for around 20 years, and for the longest time has really had a big focus on keeping your data safe, on being a reliable thing to store your data in and not lose it, right? Coming back to those really hardcore kind of ACID semantics.
Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/SEDaily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SEDaily. It would support Software Engineering Daily, and it would introduce you to the world of automated investing. Wealthfront.com/SEDaily. Thanks to Wealthfront for being a continued sponsor of the show. Now, let's get on with the show. You have mentioned that Postgres is much more than a database today. You've described it more as a data platform. Can you explain what you mean by that? How has it evolved from what you would typically classify as a database to a data platform?
Sure. So I look in Postgres is a data platform, I think, in a lot of ways. So under the covers, right, it's still the same core storing your data. But what it's done is a couple things. Postgres has built some extension APIs in there that allow you to do a lot of interesting things and hook directly into the core of Postgres, which has been pretty powerful. And maybe we'll come back to that a little bit more. But it basically kind of, I think, is a little bit of the future of Postgres and where it's going. But from a platform perspective, Postgres is, first of all, for a number of years taken a very liberal approach to data types. I look in Postgres was probably the first NoSQL database in that it had an XML data type. I believe it was like 7, 8, 9 years ago. So at that time, you could store, XML documents directly in your database. I think there were a number of XML-only databases, and over time, those just faded away, and Postgres said, sure, we'll just add this data type. But it's also done that with newer types. One of my favorite ones is arrays. Not always needed, probably not as quite as exciting as JSON, but arrays can be really handy if you're doing something like a blog application and you just want to have tags, right? You don't necessarily need a whole lookup table for that. There's no point for it. So if you're using arrays in your application, they might work just fine in your database. The more popular one everyone gets excited about is JSONB in Postgres, which is a binary JSON data type. So if you want to do a complete document store, you can do it directly in Postgres and have all those transactional guarantees. Postgres has also taken a pretty liberal approach to index types. So now there's not just the standard B-tree index, but there's a new set of indexes almost every release in Postgres. These usually come from a group within the Postgres community, commonly known as the Russians. So there's a group of hackers over in Russia that will come up with a crazy idea for a new index type. For example, I think the latest one was BRIN, block range indexes in Postgres. They're useful if you have data that naturally clusters together of over 1 billion records in a row. So maybe something like phone numbers, right? Where you've got an area code prefix first, then you've got some common 3-digit prefixes, then the 4 numbers. So they're naturally clustering together. Usually they show up and have a crazy idea for an optimization. No one thinks it'll work. They disappear for a few months and they show up with code that's ready to commit. So, I mean, that's one area. I think I look at the extensibility of indexes. But on this index side, there's a lot happening there. So there's things for full text search. There's things for geospatial. There's things like Citus, which allow you to turn Postgres into a distributed database. There's foreign data wrappers that let you connect from inside Postgres to another system, like an Oracle, like Mongo. So within Postgres, you can directly query one of those systems. So I look, and all these things that are happening on the periphery means you don't necessarily have to write C code. You don't have to get it committed to the core of Postgres. Postgres is more and more advancing with the same underlying foundation and data guarantees, but adding a lot in the user experience side and just functionality in general without that high overhead of kind of committing C code into the core of Postgres, because there is an extra barrier there in terms of code quality and what you've got to do.
Could you give me some backstory on how the Postgres community developed relative to the MySQL community? Because you've just said that they came from similar roots. Where did the diversion happen?
It's a good question. I don't know if I can go all the way back. Postgres is pretty interesting in that it was formed by a non-profit foundation which no one owns. So I think that's one especially interesting thing. You look at Postgres, and no one can ever own Postgres. I think it's been in the news a little bit with MySQL and some other databases. Like MySQL was created by a company as a layer on top of another underlying system to add SQL. Postgres started without SQL, and then it was layered on, but it was always still an open source database that was owned by no individual. So in that sense, I think it's pretty unique in that it is one of the largest open source projects not owned by any person. But it's grown pretty gradually and slowly over time with a set of, there's a core committer basis. That's a small handful of people. I'm not actually sure how many people are considered on the core team now, but last I knew it was around 7 or 8. And then there's people that actually have a commit bit to Postgres. That's a little bigger. My guess would be around 30 to 40, and those are major committers. And then there's what's known as minor committers. So it's got this pretty big community of hierarchy that, one, ensures that the code quality is up there, but then also has this process kind of for gradually committing and becoming more and more involved in Postgres.
So why do people choose Postgres in contrast to these other options for relational databases? If you're starting a company, you can look at the landscape of relational databases. How should you evaluate which one to pick?
Sure. It can definitely be, I think, pretty confusing if you look at the landscape that's out there. I mean, I'm obviously biased towards Postgres because it is entirely open. You don't have to worry about any company going away. The community's there and robust and been there for a long time. So I think that's one thing if you do worry about what happens, if that company goes away. But there is the other side of, how usable and flexible is it? If you're doing geospatial stuff, Postgres is usually one of the default databases to choose because it is so robust and flexible. I think you really need to look at the feature set and what you're trying to do there, right? A common way I approach this is from the language you're building in. So while it's great for Postgres to be a really powerful database, some languages play really well with it. Others are still maturing, if you will. So I look at some like Python and in particular the Django community. Django almost requires you use Postgres. I don't think they'd ever say that publicly, but if you look, it's a very, very strong focus on making sure that Postgres works really well. It's well supported. It's the database that pretty much all people in that community use. Rails is another one that's very strong. I look at something that's maybe less strong, and I think it's PHP. PHP had a really strong tie to MySQL for a long time with that LAMP stack. So I think it's still kind of catching up in some ways with all of the extra tooling and libraries and that kind of thing. So I would look at, first, what kind of license do you need, if that's a strong requirement for you. Then two, the feature set. If you need strong JSON support or full text search or geospatial, Postgres can be a good fit. And then I'd also take into effect, how rich is the ecosystem for Postgres in the language you're working with. Now, if you want to pick your language based on a love for Postgres, I'm perfectly okay with that too. Interesting.
So Uber recently migrated from Postgres to MySQL, and in the last few weeks, there's been a number of posts about this. This is, I read into this a bit, did some research, and this is the most I've ever gone into the weeds about how databases work. And I was surprised by. I actually found it pretty interesting, pretty entertaining. I now understand why people work on databases. But what was your response when you saw the blog post about this?
So my first reaction was a little amusing for a couple of reasons. First, and I could be wrong on this, so don't quote me even though we're being recorded here, but I believe they actually made the switch about a year and a half ago. And it coincided with a new VP of engineering coming in. I do also kind of like look through their list, and I'll get a little bit, I think, into some of the posts here in a minute. But I also look, with a new VP of engineering that really liked MySQL, okay, that makes a lot of sense. I also find it amusing that they had an almost identical post about 3 years ago of their switch from MySQL to Postgres. So it's not the first time they wrote a post about moving from one database to another and the flaws of it.
Right. I think for the context, they started out in Postgres, or they started out in MySQL, and then they switched to Postgres so that schema updates would be faster, so they could update their schema with less problematic effects. And now they're switching back to MySQL.
Yep, and I believe they actually made the switch a little while ago. And now they were, burnt by a couple things. In particular, I'm very pleased with the Postgres community's response there, because while there were a couple of blog posts kind of dissecting the issues, I think the Postgres community took an honest look and said, okay, this isn't an issue, this isn't an issue, but this, we can do better on this, and we can do better on this. I think their case was pretty interesting. At a high level, it really sounds like they built a complete NoSQL layer on top of a relational database, which I kind of wonder why use Postgres or MySQL at that point. But I haven't gotten to sit down with the team myself and kind of drill into that. So I think it's interesting. But at the same time, some of the issues they ran into, some of them were painful for them at the time. and some of them have been fixed since, and some of them Postgres the community can definitely do a little better on.
So, do you have an understanding of like what were the problems that they ran into? Like, can you articulate them? I mean, there'll be an episode with Evan Klitsky, the guy that wrote the post, so we will have this in more detail. But it's kind of a complex set of issues. So maybe you could explain it from your point of view, or what you have what your interpretation of the problems that they encountered is.
Yeah. So, I mean, I think the first one, and I'd love to actually hear the interview with Evan. I think the first one is they encountered a bug that basically replicated corruption from one node to another. That left a pretty bad taste in their mouth. Anytime you have something that's supposed to be safe for your data, corrupt it, that's unfortunate. That was around Postgres 9.2, I believe. So that was a release that was 4 years old right now. I actually vividly recall this because we ran into the exact same issue when I was at Heroku, and we dug in pretty well. We actually recovered everything. We're completely fine, but it wasn't fun. But the Postgres community actually fast-tracked a release much faster than they normally do in that case because it was a pretty serious bug. As a result of that, the community went and did a little bit of kind of fundraising. Heroku wrote some checks. Some other people did as well to do a little extra around testing of data corruption, replication of the wall, that sort of thing. So that definitely was an issue and a bug they hit, I guess 4 years ago, but it was quickly fixed, and the community took a pretty quick response to addressing the ability to test that sort of thing. I can't say it'll never happen again, right? It's software and bugs happen. But there's extra testing and kind of tuning around that and monitoring to make sure it doesn't happen going forward. So I think that was one thing that definitely left some bad taste in their mouth, and I can understand why. The other one, I believe, is kind of there's probably two issues right there that are slightly tangled together. So one is around some of what we talked about earlier, the Rightahead log in Postgres. And it sounds like for their workload, there are a lot of updates and deletes happening, which is going to write more data into the Rightahead log. And their problem, this was causing some problem with replication overall. And go ahead. Yeah, no, that's exactly what Evan said. And he said, so yeah, Uber has a write-heavy workload. The Rightahead log, so it's the Rightahead log in conjunction with what he called write amplification, which is like when you update something in Postgres, you also update all of the indexes associated with what you're updating. But it sounded, from what I understood, you also update some other indexes. What he described as write amplification is kind of an unnecessary updating of more indexes than is necessary. And then all of those writes, not only do you have to update these indexes, but these writes get propagated to the Rightahead log, and these two things in conjunction create some bottlenecks. And then if the Rightahead log gets overwhelmed, you have a lot of problems. And then there's additional problems when the Rightahead log is getting replicated across different data centers. It just sounded like a really bad set of things happening all at once to Uber. Yep. So, and I mean, I think it's interesting, and I knew some people at Uber years ago, and they actually, were looking for Postgres DBAs and having trouble finding one. So I think,
this is one way to solve that.
There are some things, that I think could have helped in their situation, right? So Postgres, I'm trying to remember when it came in exactly, but has this idea of heap-only tuples. And so this is the case where a tuple or row is being updated very frequently. It can update that without touching any index if the new version can be stored in the same page. So in my mind, I'm very curious on if they looked at that or not, or why it would or would not work. I think they're very much a unique case at a high update and write volume. But essentially, heap-only tuples is kind of an area where the new wall doesn't have to be kind of exploded out in the same way. and it can basically do it kind of by reference there. That usually can work pretty well for a lot of those cases. The other fact is, I think their preference for MySQL comes down a little bit to logical replication, right? So the other way of replicating, instead of kind of this write-ahead log that has every kind of append-only action, including like writing a row when you're deleting one, is logical replication, and just replicate the statements. So you're not replicating quite as much data, and then let the statement run on that other node, right? And MySQL has had logical replication for a number of years. Postgres has had it just outside of core. So Postgres has had it as an extension with PG Logical, and I think that's one of the debates that really kicked up on the Postgres core mailing list and community mailing lists is around PG Logical of should this be in core? And I think, the agreement is mostly yes there. Logical replication isn't only nice for not kind of sending so much data across the wire. You can also do other interesting things there, like you can send only certain commands or filter things in another way or do different analysis on those statements because it is just SQL statements. So I think that was kind of one of the other big issues that they had. And, my answer there is there was a utility there. There is one. It's just not directly in the core database. But I think, when you're doing things that are pretty advanced and unique, it's perfectly fine to look at some of the external kind of tools that come around it.
Got it. So I did an interview with your fellow Citus Data employee, Özkan Erdogan. I'm not sure. Did you founded? I think you founded the company with him, or were you just an early employee?
I did not.
Oh, okay.
I only actually joined about 6 months ago.
Okay.
So before that, I was at Heroku for 5.5 years. Fairly early employee at Heroku. Most of my time there was spent running product for Heroku Postgres.
Okay.
And just came over here actually to build and launch our cloud service.
Okay. Can you contrast what are you working on at Citus, and how does that contrast with what you were doing at Heroku?
Sure. So in many ways, I'm doing something very similar to what I did at Heroku. I actually came over here and two other kind of former colleagues that were the founding engineers of Heroku Postgres came and joined me to build out the cloud service here. So I'm working with a team that's very familiar at running a database as a service. Citus, if you're not familiar, basically turns Postgres into a distributed database. So we allow you to scale from a single node Postgres across multiple nodes. So this can be if you need to need more cores for real-time analytics, need to scale out memory and just shard your database. If you've got a multi-tenant database that's outgrowing a single node and need to scale that out, we basically are an extension to Postgres that allows you to seamlessly scale out that data.
Okay.
And so over here, basically, I head up our managed cloud offering on top of AWS, which if you think of Heroku Postgres, it's a managed database as a service. You click a button, you get a database. We take care of kind of a lot of those things I talked on before of like archiving the wall to S3, making sure you have backups, monitoring it, so make sure it's up and available, high availability. So if you want it, basically we're running a standby for you, can automatically fill it over for you. All those things that Heroku is doing for you, we're doing the same thing for Citus, just in a kind of more scaled out way.
All right. Well, I guess to wrap up, what is the future of the Postgres platform and the Postgres community from your point of view?
Yeah, so I think I hit on this a little bit, but I think the extensibility is going to be the big key going forward. As much as they can continue to build out those hooks and allow more people to come in and add things, I think if you look at any other language, right? If you look at Ruby, you look at Node, you look at Python, you look at any of those, the ecosystem is really in all the libraries that are around it. I think Postgres has a nice, stable platform for your data. I think, some of Uber's pains withstanding, I think the community is improving some of those, has already improved some, and will continue to. I think if we look, there's a lot of people that run it at scale already. But I think the power really comes in being able to add on, create more functionality in Postgres without its yearly release cycle. So you don't have to wait 18 months before you actually see a feature live. So I look at new data types, new languages, ability to connect to other data sources. That really is being the future. I think if you talk to a Postgres core person, they might say performance as well. I think, every database person does care about performance. But I also feel it's at a pretty good standpoint already in terms of performance overall. So I think while performance will continue to improve, it's all of these kind of external pieces in the form of the extension ecosystem that's really the future. And I think if you want to look at where to find them, one place, Postgres Weekly, is a weekly email newsletter I curate. pgxn.org is a website where there's a repository of Postgres extensions. And then, of course, GitHub. There's a number there as well.
All right, Craig. Well, I want to thank you for coming on the show and talking about relational databases and Postgres and Uber and all the things that we covered.
Yeah, absolutely. Thanks for having me. It was a great time.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow.